what you have to understand is that the contacts, okay, provided at base terminal, emitter terminal, or to that matter, even at the collector terminal, is made up of metal, right? The metal contacts have been provided at the three terminals of the transistor. Now, these metal contacts are provided so that an external circuit can be formed, right? But what happens is that during the transistor operation, okay, the base terminal, okay, will be at some voltage VB, all right, and the emitter terminal will be at some voltage VE, okay. So base terminal will be at some voltage VB and emitter terminal will be at some voltage VE, okay. Now, both base terminal and emitter terminal are made up of metals. So what I will do, I will try to show you the equivalent circuit. This is your base terminal and this is your emitter terminal. Now, between base and emitter, what do you have? Between base and emitter, you have the medium as air. Are you following? Between base and emitter terminal, the medium is air. So, between the two metal electrodes, you have air. And air is a dielectric medium, right? So air is an insulating medium. Air is an insulator. So indirectly, there exists a parallel plate capacitor or a simple capacitor because you have two metal contacts and these two metal contacts have been separated with air. Air is acting like an insulator. So there exists a capacitance effect between the terminals of the device. Okay, so there exists an inter-electrode capacitance. Since these two are electrodes, that's the reason this capacitance is called as inter-electrode capacitance. Capacitance. In other words, it is called as stray capacitance or parasitic capacitance. Parasite, right? Biological term. Parasitic capacitance. Okay. So parasitic as in, to the naked eye, that capacitance doesn't, see. I mean, you will not be able to see using your eyes, but there exists, and its effect can be felt when we carry out something known as frequency analysis. So that's the reason the name is given as parasitic capacitance. So this parasitic capacitance exists between base and emitter terminal. It also exists between collector and emitter terminal, okay, and it also exists between base and collector terminal. So BC. Okay, and this is CDE. DE. So these inter-electrode capacitance for a common emitter configuration, okay, you can say there are three: base to emitter, collector to emitter, and collector to base. Collector to base. Okay, BC or CB doesn't matter. Okay, so this is called as the inter-electrode capacitance. Now, the Miller effect capacitance is nothing but the capacitance which is the largest amongst the three. Okay, so that is this capacitance, base to collector capacitance, or capacitance found between the input terminal and the output terminal. Okay, see, this is your input capacitance, right? Base to emitter. Okay, and collector to emitter is kind of output capacitance. Okay, but collector to base capacitance is the capacitance measured from the input base terminal and the output collector terminal and that capacitance is the largest capacitance in comparison with the other two. So this effect is observed by a telecom engineer called Miller. Hence, the name is given as Miller effect capacitance. Miller effect capacitance. Now, the effect of this Miller capacitance is that it modifies overall input and output impedances. The effect of Miller capacitance is something like it modifies input and output impedances, due to which gain gets, or we can say voltage gain gets modified, and hence performance is disturbed. Okay, so this is a very short discussion about the stray capacitance. Okay, now let us look into the Miller capacitance. Okay, but did you understand, or at least did you get the feel of it, how exactly this parasitic capacitance comes into picture? Now, the effect of parasitic capacitance is negligible at low frequency. Okay, that's because Xc is inversely proportional to F. So when frequency is low, Xc is very large. So your parasitic capacitance is open circuit at low frequencies. So your parasitic capacitances can be regarded as an open circuit element, at low frequency. But at high frequency, you cannot treat them as an open circuit element. Okay, that's because at high frequency, the reactance is very low. Okay, so at high frequency, parasitic capacitance behaves like short circuit elements, and therefore it creates virtual shorts in transistor circuits. Therefore the gain gets reduced. Okay, this is very important for Viva as well as in the competitive examination. Okay, so they may ask what is the major cause for dip in voltage gain in the high frequency region. So dip in voltage gain in the high frequency region is attributed to the presence of parasitic capacitance, and at higher frequency the parasitic capacitance is very, very small, so it can be treated as short circuit element. So there exists multiple short circuits across the transistor terminals. Okay, there will be a short circuit between base and collector and emitter, and base and emitter. So due to this virtual short, the voltage gain gets reduced, and the overall gain will be much lower in comparison with the expected value. So this is the effect of parasitic capacitance. The frequency is smaller, hence reactance will be a lot larger. Hence, the parasitic capacitors can be treated as open circuit elements. Okay, whereas in the high frequency region, high frequency region in the sense frequency which normally varies in the range of megahertz. Okay, so when the frequency is high, the reactance offered by these parasitic capacitances will be a lot lower. Okay, so that's the reason, you know, these capacitors are taken as short circuit elements, right? Because when the reactance is small, you can consider that reactance as a short circuit element. Okay, so due to the effect of virtual shorts, okay, across the transistor terminals, pictorially, you know, you can represent something like this: the high frequency phenomenon. Okay, let's say this is your transistor driven in common base configuration. Okay, so in the high frequency region, you know, something of this kind will happen. Okay, indirectly, all the electrodes, okay, will be short circuited due to parasitic capacitance. Due to parasitic capacitance. So due to this effect, what happens is that voltage gain dips, and obviously the amplification will not be that good because of the dip in voltage gain. Okay, all right. Now today let us look at the analysis aspect of parasitic capacitance. Okay, all right. So let me start with Miller effect capacitance. So since this was observed by a scientist called Miller, hence it is also called as Miller effect capacitance. Okay. So as I said in the beginning, that in a high frequency region, reactances of coupling capacitor, input coupling capacitor, output coupling capacitor, and bypass capacitor will be very small. Okay, will be very small, and therefore for the analysis sake, these can be replaced with the short circuit elements. Okay, short circuit elements. On the other hand, inter-electrode capacitances. Inter-electrode capacitances that are nothing but, you know, these capacitances: CBC, CCE, and CBE. Okay, inter-electrode capacitances and wiring capacitances. Okay, wiring capacitances. So these wiring capacitances are nothing but the capacitance effect caused due to the physical mounting of wires, right? You will be using several wires to connect different parts of the amplifier circuit. So, you know, these wires will be at some potential. So, you know, once again, there will be a capacitance effect felt between these wires and the ground terminal. So this is called as wiring capacitance. So inter-electrode capacitance and wiring capacitances, okay, comes into picture in the high frequency region. For high frequency. Okay. Now, the capacitance found between base and collector junction is called as Miller capacitance. Miller capacitance. Okay, so base and collector is this one. This is your Miller capacitance. Miller capacitance. Now we'll be paying attention to Miller capacitance because this Miller capacitance, okay, let's say CBC, which we will take it as, you know, Miller capacitance. So this CBC is very big in comparison with CBE as well as C. Okay. So out of the three capacitance effects, this Miller capacitance is the largest capacitance compared to the other two. All right, fine. So the effect of Miller capacitance. Okay. So what is the effect of this Miller capacitance? So effect is something like it will increase. Okay. Output and input capacitances. Due to which Zi and Z0 gets altered, and the end effect would be something like reduction in voltage gain. I think I have already told you. Reduction in voltage gain. Okay. So this is the definition of Miller capacitance. The capacitance found between base and collector junction is called as Miller capacitance, and the Miller capacitance is the highest. It is having highest capacitance value in comparison with the other two, and the Miller capacitance basically alters the input and output impedances by increasing the output and input capacitances, due to which there will be a reduction in voltage gain. Okay, fine. Now let us look at the theoretical aspect. Derivation, let us consider. Okay, so for derivation, what we will do is we will consider a transistor black box. Okay, and let us mark the terminals. Input terminal, the output terminal. Okay, so this is our transistor whose voltage gain is output by input, the no load voltage gain. Okay, now let us show the Miller capacitance. Okay, as I have told you, Miller capacitance is the capacitance found between input and output terminal. Okay. So this is your input terminal and this is your output terminal. 1 dash, 2 dash. All right. So this is your output V0 and this is your input Vi. Okay. So let us define certain things over here. So let us define Ri as the input resistance of the black box, and let us define Zi as the overall input impedance of the device. Okay, so let us take this capacitance as CF, and CF is nothing but feedback capacitance. Why feedback capacitance? Because it connects the input terminal and the output terminal virtually. That's the reason it is called as feedback capacitance. Okay, all right. Once you are done with this, what you can do is you can mark the current directions. Okay, let's say this current is II. Okay, II, and this current II will divide into two parts. The upper part, let's call it as I2, and the component of current which gets into the black box, we shall take it as I1. All right, fine. Next, let us apply, KCL. So apply KCL at node A. Okay. So when we apply KCL, what do we get? We get input current II is equal to summation of I1 and I2. All right. Let's take this as equation 1. And what is II? So II can be taken as Vi by Zi, where Zi is the overall input impedance of the circuit, and I1, okay, I1 is basically the current which is getting into the black box. Hence, I1 can be taken as voltage remains the same because it's a parallel combination divided by Ri. Why? Because Ri we have taken as the resistance of the black box. electrons. Okay, so that's your Ri. And similarly, you can also find an expression for I2 on the basis of nodal analysis, because I2 is under the influence of um, Vi as well as V0. Okay, where V0 is your output voltage. So I2 can be written as difference in potential, that is Vi minus V0, divided by the reactance of the capacitance. So let's take the reactance as XCF. Okay, so reactance is equal to XCF. Okay, right. So we have written different expressions for different currents. Now let us substitute them. So we get II is equal to Vi by Zi is equal to I1. So I1 is Vi by Ri plus I2. What is I2? Vi minus V0 divided by XCF. All right. So let's say this is equation 2. Then also we have V0 is equal, sorry, not V0. AV is equal to V0 by Vi, or you can write V0 is equal to voltage gain times the input voltage. Okay, so output voltage is voltage gain times the input voltage. We shall take it as equation 3. Then substitute 3 in 2. Okay, that is somewhere over here. So you will get Vi by Zi is equal to Vi by Ri plus Vi minus V0. Okay, against V0, what you can write? Gain times input voltage you can write, right? Divided by XCF. Okay, or that is equal to Vi divided by Ri plus, take Vi outside the bracket, that is 1 minus AV divided by XCF. All right, so that's the simplified expression. Okay, now what you can see is you can cancel out Vi from both sides. Okay, you can cancel out Vi from both sides. So what do you get? 1 by Zi is equal to 1 by Ri. Okay, this is what I meant to say. You can cut this Vi with this Vi as well as this Vi. So this becomes 1 by Ri plus 1 minus AV divided by XCF. Okay, or this can also be rewritten something like this: reciprocal of resistance plus, what I will do, this numerator term 1 minus AV, I will try to shift to the denominator. You see how it is done. 1 divided by, I'll write XCF, okay, divided by 1 minus AV. No harm done, right? Because this 1 minus AV is still sitting in the numerator itself. Okay, fine. Now, where XCF, okay, where XCF is basically 1 by 2 pi FCF, right? And 1 by 2 pi F is nothing but omega. So XCF can be taken as omega, okay, this is omega into CF. Okay, so we'll try to substitute 1 over omega CF in this particular equation. Okay, so we get 1 by Zi is equal to 1 by Ri plus 1 by basically, okay, what I will do, let me show the intermediate step. Let me not skip the step. Okay, so I have this term, right? Okay, let me just shade this term and let me rewrite this term. XCF divided by 1 minus A. Okay, this can be written as 1 divided by, because XCF I have already written, right? What is XCF? 1 divided by omega into CF. So let me write it, omega into CF into 1 minus AV. 1 minus AV. Okay. Now, what we will do is, this we will take it as, see, 1 divided by omega CF into 1 minus AV. This we will take it as some new reactance XCM. New reactance XCM. Okay. So where XCM is equal to 1 divided by omega CF into 1 minus AV. Okay. So therefore, Zi is equal to 1 by Ri plus, okay, here it is 1 by Ri plus 1 divided by this term, the term which I have placed within the cloud, that is XCF divided by 1 minus AV. What is it? We have got it as XCM. So you can directly substitute it as XCM. All right. So we shall take that as equation 4. Okay. Now, if you look at equation 4, you would see that the overall input impedance Zi is comprising of 2 elements, resistive element and an reactive element. So basically, equation 4 represents a parallel circuit. Comprising of Ri and XCM. Okay, Ri and XCM. Okay, so you can construct a parallel circuit out of equation 4. That will be something like this. So you have Ri in parallel with Miller capacitance, okay, whose reactance is XCM. Okay, so this XCM can be written as CMI, okay, Miller input capacitance, which is equal to, here it is, 1 minus AV, into CF. Okay, 1 minus AV into CF. So this also I will show you. Okay, so this particular product, we are taking it as Miller input capacitance. Okay, CMI. And this is your VI. Okay, and okay, so this is the thing. So this is the equivalent circuit when we consider Miller effect capacitance. Okay, now the effect is something like this. Okay, for low frequency, okay, the Zi would have been Ri. Okay, since there is no parasitic capacitance effect comes into picture for low frequency. But for high frequency, Zi is not equal to Ri. Instead, Zi is basically parallel combination of Ri and XCM. Okay, where XCM is the Miller capacitance here. Okay, so this is the effect what you are supposed to observe. Okay, so that's your input Miller capacitance. Okay, fine. Now, what we did so far, we analyzed the Miller effect capacitance from the input side, but this can also be observed from the output side. Okay, because what happens is that in case of transistors, we won't be taking only single stages, right? We will be taking the multi-stages also, right? That's because when the gain of one single amplifier is not sufficient, what we do is we try to replicate, multiple, we try to replicate the first stage in the second stage as well as in the third stage. So due to this cascading effect, there can be, capacitance effects exists in the output side also. Okay, so now what we will do is we will try to derive an expression for Miller capacitance by looking at the output terminal. Okay, so that we will call it as output Miller capacitance. Okay, so analysis remains the same, just that we are going to change the current directions. Okay, so now we are looking from output terminal to the input terminal. So let's say this is your input port. Say this is your output port. This is V0. Okay. And this is your feedback capacitance. CF. Okay. And this is your VI. Now, over here, what we are trying to do is that we are carrying out the analysis from the output node. So let's take this as I0. Okay. So this I0 will divide into two parts. Okay. One from the upper part and one from the straight part. Okay. So this part we'll take it as I1, and the top portion of current we shall take it as I2. Okay. And the gain of the transistor is still the same, that is AV is equal to V0 by Vi. Right. And let us define certain things. Okay. Let us say R0 is the resistance, output resistance of the amplifier. The black box. R0 is the output resistance of the black box, and Z0 be the overall output impedance of the transistor network. Okay. Since voltage is known, okay, you can write an expression for I1, I2, etc., etc. Okay, so we can write I1 as I1 as voltage by resistance, V0 divided by R0. Similarly, we can also write I0 as voltage divided by overall impedance, Z0. And we can also write I2 as difference in potential, because CF connects V0 as well as Vi. So basically element CF, it is under the influence of input voltage Vi as well as output voltage V0. Since we are taking out the analysis from the output side, so we shall write V0 minus Vi, okay, divided by XCF, okay, just like in the previous case. Okay, or I2 is equal to, now V0 can be taken as, we want output V0. That's because our analysis is starting from the output side. So you see here, I2 is equal to, okay, let me retain V0 as it is, minus Vi. So I know that V0 divided by Vi is equal to AV. So that means to say input voltage Vi is nothing but output voltage divided by the voltage gain. The same thing I'm going to substitute here. So in place of Vi, I'm going to substitute V0 divided by AV, okay, divided by XCF. Okay. Then apply KCL at, let's say, node A. Okay, at node A. So you would get I naught is equal to I1 plus I2, which is equal to I1. I1 is V naught by R naught plus I2. You have a simplified expression. So what I will do, I will take out V naught outside the bracket. So if you take V naught outside the bracket, you are left with 1 minus 1 by AV divided by XCF. Okay. So take this as your equation 1. Okay. One approximation we can propose here. Okay. Since R naught is very large, okay, typically in the range of up to 40 kilo ohm. So what you can do is you can approximately write I naught, okay, as, so this is this component. No, I naught is equal to I2. Okay. Therefore, I1 is very small. Okay, when R naught is very large, so the component of current which gets into R naught will be a lot smaller. Hence, you can neglect it off. So you can simplify the analysis. So I naught is approximately equal to I2. So that means to say I naught is V naught by Z naught, as stated earlier here. Okay, I naught is V naught by Z naught. Here I have written, right, V naught by Z naught. Okay, which is approximately equal to I2, and I2 is here. This is I2. This is I2, and this is I1. I1 we have neglected, so which is approximately equal to V0 into 1 minus 1 by AV divided by XCF. So you can cancel out V0 from both sides. So basically, your output impedance, is greatly affected by the Miller capacitance itself, right? Miller capacitance itself. So 1 by Z0. So what I will do, I will shift this numerator onto the denominator side. So let me write 1 divided by XCF divided by 1 minus 1 by AV. 1 by AV. Okay. So that is also equal to 1 divided by, what is XCF? We know that XCF is equal to 1 by omega into CF. Okay. We will substitute this here. So you get 1 divided by 1 by omega CF into 1 minus 1 by AV. Okay, AV, where this term CF into the gain term. Okay, CF into gain term, we can take it as new capacitor CM. Okay, I'm not including frequency, because if I include frequency, it becomes reactance. So I'm just collecting the capacitance term with the gain term. Okay, gain is unitless, right? So it just gets multiplied, that's all. So CF times 1 minus 1 by AV, let us define it as CMO, where CMO is equal to output Miller capacitance. Output Miller capacitance. Okay. Also the product 1 divided by omega into CMO is equal to 1 divided by omega into CF into 1 minus 1 by AV, okay, can be taken as XCMO. Okay, XCMO. Therefore, 1 by Z naught is approximately equal to 1 by XCMO. XCMO. So you can observe clearly that your output impedance is equal to the reactance of the Miller capacitance. Miller capacitance. All right. So you can write CMO is equal to F EAV. Okay. So you can say that output impedance is approximately equal to Miller output capacitance. Okay, so that's how it alters the impedance, and as an end effect, the gain is going to get altered. Okay, that's because your capacitor is actually directly related to the transistor gain EAV, the voltage gain. Okay, I'm not talking about current gain, it is about the voltage gain. So this is the effect of Miller capacitance. Okay, it basically alters input and output impedances. Okay, so just to summarize, okay, we found the Miller input capacitance, and the Miller input capacitance is found to be CF times, basically it is 1 minus EAV, okay, and the Miller output capacitance found to be CF times 1 minus reciprocal of voltage gain. So this is your end result. Okay, end result. All right. So normally this derivation will be asked for 6 to 8 marks. Okay. Is it understood? Do you have any doubts? Do you have any doubts?
No, sir.